Hello everyone, myself Shweta Shah, Assistant Professor at L.J. Institute of Engineering and Technology, Computer Department. We are here for the subject Computer Organization and Architecture. We are starting with Unit 1, that is Computer Data Representation and Register Transfer and Microoperation. In this unit, we are going to cover these topics like basic computer data types, complements, fixed point representation, floating point representation, register transfer language, register transfer, bus and memory transfer, arithmetic microoperations, logical microoperations, shift microoperations, and arithmetic and logical shift unit. Okay, let me start with our first topic, that is basic computer data types. Data are nothing but numbers and other binary coded information that are operated on to achieve our required computational result or our goal. Okay, there are many number systems are available like binary number system, decimal number system, hexadecimal, octal, BCD, etc. Okay, for any number system, the base or radix of the system is represented by R, and that represents how many distinct symbols are available for this number system. Okay, for example, if we consider a decimal number system, then we have radix 10. That means it has a total 10 different symbols to represent the any number, that is 0, 1, 2, 3 up to 9. Okay, similarly, to determine the quantity that the number represent, it is necessary to multiply each digit by integer power of r and then form sum of all weighted digits. What it means? It means that if you want to for example, if you want to represent this number 724.5 in a decimal number system, we know decimal number system has a radix 10, or you can say base 10. And here for number 724.5, 4 is at 0th position, 2 is at first position, 7 is at second position, and 5 is at -1th position. Okay, so similarly, if we want to represent this number in form of its base and its power equivalent form, then we can represent it as for this 7 we have to multiply this by its position power. It is at position 2 and its position power will be 10 raised to 2. As we are using decimal number system, so power will be 10 raised to 2. For 2, it is at a position 1, and as it is a decimal number system, so power will be 10 raised to 1. For 4, 10 raised to 0, and for 5, 10 raised to -1 according to its position. Okay, and to finally get the representation, we have to add this all of this multiplied content, like 7 into 10 raised to 2 plus 7 into 10 raised to 1 plus 4 into 10 raised to 0 plus 5 into 10 raised to -1. Okay, so this is our our representation of any decimal number in terms of its base and its power form. Okay, if we consider a binary number system that has a radix 2, that means it has only two symbols 0 and 1 to represent any number. For example, if we consider a string 101101, okay, to represent this number, its or to represent its decimal equivalent number, we have to multiply each 1 and 0 with power of its radix. Okay, for example, 1 is at position 0, 0 is at position 1, this 1 is at position 2, this one is at position 3, this 0 is at position 4, and this 1 is at position 5. So to find out its equivalent number, we have to multiply this 1 with 2 raised to 0, this 0 with 2 raised to 1, this 1 with 2 raised to 2, this 1 with 2 raised to 3, this 0 with 2 raised to 4, and this 1 with 2 raised to 5. And lastly, we will do summation of all of this multiplied term. And if we equate these, then we will find as a 45. So it is our decimal equivalent of binary number 101101. This is also 45, this is also 45, but it is in a decimal number system and this is in a binary number system. Apart from this binary decimal system, decimal number system or binary number system, we are using octal number systems, hexadecimal number systems, BCD number systems, etc. Octal number system is a radix 8 system. That means it has a total 8 symbols to represent different numbers. Okay, and that this 8 symbols are 0, 1, 2, 3 up to 7. Similarly, for hexadecimal number system, we have this numbers as 0, 1 up to 9, this 9 decimal numbers, and then A, B, C, D, E, and F. Total 6 alphabet. Okay, that means it has a total 16 symbols to represent any number. We can represent this. This is shown over here. For example, you have octal number 0, 1, 2 up to 7. Then it has its equivalent binary as a 0 has its equivalent binary as a 000, 1 has a 001, 2 has a 010, and 7 as a 111. Okay, like this. Now, what if you want to represent any number like 24? How you can represent this? So for that, you have to represent 2 in octal number system, 4 in octal number system differently. Okay, 2 we can represent it as a 010. 4 we can represent as a 100. So we have number as 010 and 100. Okay, for any octal number you can represent like this. You have to represent one octal number at a time in form of binary. Okay, similarly for hexadecimal number system, you have total 16 symbols that are 0 to 9 and A to F, and its binary equivalent is for 0 you have 0000, 1 00001, A 1010, F 4 times 1. Okay, these are your binary coded hexadecimal representation of this hexadecimal numbers. Okay, similarly, as we have seen in octal number, if you want to represent this number like 63 in a hexadecimal equivalent binary coded hexadecimal system, so you have to represent 6 as a separate hexadecimal number and 3 as a separate hexadecimal number. So for 63 you have to represent 6 as a 0 110 and 3 as a 0011. Okay, so like this you can represent any hexadecimal number in a binary coded hexadecimal number form. Okay, one more system we are using is a BCD number system, in which we have 10 symbols that are 0 to 9, and we are representing each number in form of 4-bit binary coded number. Okay, that means 4 is represented as a 4 times 0, 1 as a 0001, 2 as a 0010, and 9 as a 1001. Okay, now what if you want to represent 10? If you want to represent 10, then you have to represent 1 differently, 0 differently. That means you have to represent 1 by 0001 and 0 by 4 times 0. Similarly, for 99, you have to represent 9 differently, 9 as a 1001 and 1001. So by using this method, you can represent any BCD number, any decimal number into its equivalent binary coded decimal number. Okay, this is a simple system. Okay, So we can basically use a BCD number system, hexadecimal number system, octal number system, binary number system, or decimal number system. Okay, these are the different methods to represent your data. Okay, next topic we are going to see is a complement. Okay, complements are basically used to perform subtraction operation. For any number system with base r, there is two type of complements are possible, that is r's complement and r minus 1's complement. If we talk about binary number system, then it has a base 2, that means it has a 2 minus 1 and 2's complement. 2 minus 1, that is 1's complement, and r's complement, that is 2's complement. That means it has a 2's complement and 1's complement. Okay, so how you can find out this complement? So find out this complement, we can use this method. For finding 1's complement, you can find out 1's complement of any binary number system by just complementing zeros and ones in that binary number. Okay, so you have to put 0 in place of 1 and 1 in place of 0. So by that you will find out 1's complement. And to find out any numbers 2's complement, you have to first find out 1's complement and then add 1 to its result. Okay, that means you have to add 1 to its 1's complement. So you can find out its 2's complement. For example, if we have any binary number like 1 1 0 1 0 and you want to find out its 1's complement, so how you can find out? Just by complementing ones and zeros. 0, that means you have to put as a 1, 1 you have to put as a 0, 0 that means you will put as a 1, this one as a 0 and this one as a 0. So for number 1 1 0 1 0, you have its 1's complement as a 0 0 1 0 1. Okay, so it is nothing but just a complementing number, 0 in place of 1 and 1 in place of 0. Okay, to find out its 2's complement, we first have to find out its 1's complement, that we have already find out, and then have to add 1 to it. If we add 1 to 1, then it is summation of 1 plus 1. For binary numbers, 1 plus 1 is equals to 0 and carry 1. Okay, and then 1 plus 0, that is 1, 1, 0 and 0. We are doing just addition of binary 1 to our 1's complement, and then we can find out its 2's complement. Okay, this is a easy method. For 1's complement, you have to just complement ones and zeros. For 2's complement, you have to add 1 to its equivalent 1's complement. Okay, and you have find out its 2's complement. As we are discussing about binary number system, so for us 1's complement and 2's complement are important. Okay, we are continuing with next topic, that is our fixed point representation of number. Okay, when an integer binary number is a positive, any number is a positive or negative, how we can find out? We can find out by its MSB bit. If its MSB bit is 1, that represents that this number is negative, and if its sign bit is 0, that is if number has a MSB bit as a 0, that means this number is a positive. And if its a sign bit is a 1, that means MSB bit is a 1, that represent that this number is a negative. Okay, so just we can use this method to represent number is positive or negative. Okay, for positive number, you can represent MSB as a 0 and all other numbers as its equivalent binary number. That is okay for a positive number system. But for a negative number, you have to represent MSB bit as a 1 and rest of the bits as a one of this form.
This like sign magnitude representation or sign 1's complement representation or sign 2's complement representation. How it is done, let me see. For example, if you have a number plus 40, okay, so 14 has a binary representation of 1110, okay, 1110, but as we are representing it in an 8-bit number system, so we have to put 4 times zeros in MSB position. So this is our total 8-bit number to represent number plus 40. Okay, this is our plus 40 number. Here you can see sign bit is represented as a 0. That means this number is a positive. Okay, so now if you want to represent number minus 14, so how you can represent this? So for that, first condition is that you have to put MSB bit as a 1. Okay, that will show that this number is a negative number. Okay, and rest of the 7-bit, this rest of the 7-bit you have to represent any of the with any of this 3 method as a sign magnitude representation or sign 1's complement representation or sign 2's complement representation. How you can achieve this? For sign magnitude representation, you just require to put rest of 7 bits as it is. Okay, you can see rest of 7 bits are put as it is, just the sign bit is changed from 0 to 1 to represent negative number. Okay, for 1's complement method you will put MSB bit as a 1, that is okay, but rest of the 7 numbers are represented as a 1's complement of the original number. Okay, our original number, or you can say plus 14 representation contains 7-bit as a 3 times 0, 3 times 1 and 0. Okay, in 1's complement method you have to represent this 7 bits into its equivalent 1's complement. That means 0 in position of 30 you have 31, in position of 31 you have 30, and in place of 0 you will have 1. Okay, and for similarly for sign 2's complement method you will put MSB bit as a 1 as a rule, and rest of the 7 bits will be represented as a 2's complement of the original number. Original number is 0001110, and its 2's complement will be adding 1 to its 1 complement, that will be 1110010. This is its 1's complement. If you add 1 over here just in this 7 bits, just in this 7 bit, you will not consider this 8 bit. If we add 1 to this 7 bit, we will get 0 1 0 0 1 1 1. Okay, and 1 as a sign bit as it is. So this is our representation of minus 40 by 3 method. First method is sign magnitude, 1's complement method and 2's complement method. Okay, in all of 3 method, sign bit is 1 to represent that your number is a negative. Okay, next thing we will see one arithmetic example for a fixed point representation. For example, if you have two numbers like 6 and 13, if you want to do addition, then you will represent 6 as its binary equivalent in 8-bit form, 13 in its binary equivalent 8-bit form, and just addition 0 plus 1, that is 1, 1 plus 0, that is 1, 1 plus 1 0, carry 1, 1 plus 1 0, carry 1, and this carry will be over here, and rest of bits are 0. Okay, so this is your summation. But when your number is positive, both of these numbers are positive. What if your any of one number is negative? If your any of one number is negative, then you have to represent this number in form of 2's complement method. Okay, so you have to represent minus 6 in form of 2's complement. How you can find out? You have to consider this 7 bits. First you have to find out its 1's complement, then add 1 to it, that is its 2's complement, and put 1 as its sign bit. Okay, plus 13 as it is, because positive number we are representing as it is. For negative number you have to find out its 2's complement. Okay, and then you can do summation, so you will get answer 7. Similarly, if 13 is negative, then you have to find out 2's complement of 13. 6 as it is, and if both of the numbers 6 and 13, both of these numbers are negative, then you have to find out 2's complement of both of these numbers, for 6 also and for 13 also, and then you can do addition, and the result will be in 2's complement form. That means you are getting 1 in MSB bit that shows that this number is negative, this result is a negative and represented in a 2's complement form. To find out the original number, you have to take a second time its 2's complement. Okay, that means you have to complement this number and you will get 19, but its sign will be negative. Why? Because in summation form we are getting MSB as a 0. Okay, so by this method you can find out addition or subtraction of fixed point represented number. This is nothing but whenever you are getting a negative number, you have to represent this negative number by its equivalent 2's complement form, and then you can do addition. And if in a result you are getting MSB bit as a 1, that shows that this your number is a negative and represented in a 2's complement form. To know actual number, you have to take 2's complement of that result and put negative sign beside this number. Okay, so this will be of your actual result. Okay, so by this method you can find out addition and subtraction of fixed point numbers.
So here we are ending our session. In next session, we will discuss about floating point representation of number.